So this is the approach that AE2S and the study team took as we moved forward through the planning process for long-term water supply for the city of Brandon. The study area is basically the study area that is in the most recent comprehensive plan for the city of Brandon. And as you can see in the yellow, that's where primarily residential development would occur. And then there's also places where there's commercial and industrial more toward the north side of the community. And it turns out that as we looked at population growth and looked at population density from these residential areas, that into the time span between 2040 and 2070 is when this area fills up. And so it was appropriate to look out in that 2070 time span in order to look at population projections and also look at water demands that would occur at that time. The population projection used typical methods, and out of that came up with a maximum rate of population growth. That's sort of that brown tan line at the top. A minimum rate of population growth, or our lower end, which is the green line at the bottom. And then this blue line in the middle is really where we centered and selected our populations for the year 2045 and the year 2070. And so in the year 2045, we estimated the population of Brandon to be about 16,000, and to 2070 at about 23,000. Some of these other lines that you see here are population estimates from other studies that have been done in the past. So as the population grows, the people need more water. And there are commercial businesses in town, perhaps a small amount of industry as well. And so the water demand grows with population. And these are the demand estimates. We actually put quite a bit of focus on these demand estimates to make sure that we were centered on something that was believable, and used several different estimating techniques to come up with these demand curves. The bottom pair of curves, this dark blue and light blue curve, represent the average day flow under two conditions of treatment. The lower light blue line represents an average day production based upon the same type of treatment that you have right now, where it's basically iron and manganese removal plus HMOs for a radionuclide removal. Whereas the darker blue line represents the water demand or the water supply necessary to support reverse osmosis treatment, to treat the water so that its hardness would be similar to surrounding communities. The upper two pair of curves, the light brown and the dark brown line, represent the same concepts except for maximum day. And so if you look at the maximum day demand growth out to the future years, you can see in 2045 we're at about 5.2 million gallons per day for a system that's not using RO, and about I'm sorry, I missed that. It's 3.8 million gallons per day for a system not using RO, and 5.2 in 2070. And in a system where RO is being used, we have a flow of about 4.5 out to about 6.2 in 2070. The reason you need more water to use RO is that a certain amount of the water is wasted from that system. It contains the concentrate, contains the ions that have been rejected. So in our estimates, we were assuming that about 25% of the water approaching the RO system would be rejected. If you have RO in your home, that percentage of loss is much greater. It's probably 80 to 90 to 95% water wasted. When we put RO in a municipal system, it's staged so that it's more efficient. Okay? So the reason to estimate that additional demand is if RO is chosen as a treatment alternative, and that is one of the alternatives. You have water available to support that. We also reviewed the existing system, and you live in Brandon, you probably know about this. Let me just review it quickly for you. The treatment plant is located over by the park, just north of the park. Well number 6 is on the tree line to the south side of the park. Well number 1 is adjacent to the treatment plant. And well number 8 is being created. It's already been drilled and tested. And that's just north of well number 6. Well number 7 is also an existing well that's been drilled. There's pump and piping to connect it to the plant. And it's waiting to be used. Well number 3 is also in town, but is not piped to the treatment plant. There's treatment capability at that plant, and it's used at that well. It's used more as an emergency, a backup well in case it's needed for certain situations. Well 3, 7, and 6, and the proposed well 8 are all in the Split Rock Creek Aquifer. It's a deeper aquifer. We'll talk about that in a second. Well number 1 is in the Big Sioux Aquifer. Well 9 is being explored right now. They put down an exploratory hole. They're going to do some pumping tests and some water quality tests yet this month, as I understand. And that's just a little bit north of the treatment plant. There is a water storage tank, and that's the system. And you also have a lot of pipes and connections to people's homes. The existing treatment plant is an iron and manganese removal plant with capabilities to remove radium. And very conventional treatment facility with aeration followed by filtration. There are oxidants added, and then there's also a chemical, it's actually a suspension called HMO, hydrous manganese oxide, that has the capability to absorb manganese and also absorb radium. And so that represents the removal technologies at the treatment plant. The filter backwash solids, there are granular media filters in the plant that are backwashed routinely. Those solids are sent to the sewer and then head to Sioux Falls for treatment at the wastewater treatment plant there. Well number 8 has been pump tested and sampled. My understanding is the pump test was very successful. It sort of met the goal of production, and sampling has been done. The water quality looks very similar to well number 6. And then well number 9, exploration has been done, like I mentioned. We got together with the staff and the Water Development Committee and talked about treated water quality goals. And out of that came this list of goals. It basically means that the treatment facility and system needs to meet the primary drinking water standards, which are health-based standards that public water supplies must comply with. The list that you see here on the screen is simply the list of standards that Brandon needs to meet in rules and regulations. So we're not going to get into the details of all of those. Just need to know that Brandon's water supply has met those requirements in the past, and they tend to continue to do that. In addition to that, there are aesthetic parameter goals, and the Water Development Committee indicated they wanted to continue removing iron and manganese, and then also we're interested in total dissolved solids and hardness reduction if possible. And so that's a desire was expressed by the Water Development Committee. And so we pursued alternatives that would enable that to happen. When you think about that hardness, total dissolved solids, I think the idea was to try and develop water that was similar to the neighboring water supply systems. Brandon's hardness is in that range of 390 milligrams per liter. You can see over to the right. And if you look at this list here under Minnehaha Community, Sioux Falls, and Lincoln, Lewis and Clark, they're about 200. So Brandon's hardness is about twice the neighboring system's hardness. Those systems all use lime softening for doing hardness removal. The other factor here is total dissolved solids. You can see Brandon's total dissolved solids is in the upper 500, and these other supplies are in the 300 to 400, almost 500 range. So those are the main differences in water quality that people might notice if they use that water versus the water that comes from the city of Brandon. So the next part is to look at the source alternatives. And WSP, which was our sub-consultant, did a study, basically focused on a 3-mile radius of Brandon, looked at the aquifers, the availability of water, and so forth, and came back to the Big Sioux Aquifer, which they call the Quaternary Aquifer. And Sir Jay, you would know the history of Quaternary versus other types of geology. I have no intention to bring you in on this, but anyway, it's a name. I call it the Big Sioux Aquifer because that's familiar to me. It's a shallow aquifer. The existing well number 1 and the exploratory well number 9 for Brandon are in that aquifer. The Split Rock Creek Aquifer is deeper. It has existing wells number 3, 6, 7, and the new well number 8, which is under construction already in that aquifer. The beauty of their study is they supplied some great graphics, and I picked a couple of them out to enable us to understand what this looks like. Here you can see this lobe of aquifer material, and this is the Split Rock Creek Aquifer. This is a north to south section right through Brandon, from north up here to south over here. So looking north of Brandon, there's not a whole lot of Split Rock Creek, but there is a confining layer and then interbedded sands and gravels that make up the Big Sioux Aquifer. And so if you look here, are wells that were used from which to get these cross-sections, and you can see that the wells in the Big Sioux Aquifer are in this gravelly looking materials where those wells are drawing water from. And the wells in the Split Rock Creek Aquifer are screened in some cases throughout the depth. And each the notations on the top represents a well from which they got the geological information. So the takeaway from this is that the Split Rock Creek is a deeper aquifer. The Big Sioux Aquifer is much more shallow. It's above the Split Rock Creek Aquifer. The other information that they provided was that the Split Rock Creek Aquifer has radionuclide in it. Radium-226, radium-228 are ones that are commonly measured for the Safe Drinking Water Act purposes. And the radionuclide concentration seems to be more intense the deeper you go in that aquifer, which was, I guess, a suggestion from their study. Okay, so what about the characteristics of this? In terms of water quality, you can see the dissolved solids, the iron and manganese, the nitrate and hardness. Now, the Big Sioux Aquifer has a nitrate influence, and it's not unreasonable to think that some of that influence may come from the Big Sioux River, given that we're downstream, but it can come from other naturally occurring sources of nitrogen. And we're downstream of the Sioux Falls Water Treatment Plant, which discharges nitrate, as well as the Smithfield Wastewater Treatment Plant. Sioux Falls Wastewater, Smithfield Wastewater, both have nitrification plants, and so that's basically a source of nitrogen. But that's not to say that this nitrate has come from that. It's just that it's a potential source. Also, we have a hardness in this range of about 400, if we just remember that. Total dissolved solids close to 500. And iron and manganese, the concentration of iron a little bit less than what we're going to see in the Split Rock Creek Aquifer. WSP concluded that there, in the vicinity of Brandon, is potential for 5 additional wells to be installed there to provide up to 700 gallon per minute total, I guess you'd call it sustained yield, with from all of these 6 wells. So they pointed out that that is a potential source for the city of Brandon. But the average yield per well is quite low. As you'll see, it's quite low compared to what the Split Rock Creek Aquifer can do. As a part of their study, they also identified potential locations for additional wells. And so in this 3-mile radius area, they identified a couple of these black boxes here in which they said the aquifer had sufficient depth and potential for exploring more wells in those areas. And they focused on this one, and so you can see the enlarged area here. The treatment plant is down here at the bottom of the drawing. This is the well 9 that's being explored right now. And they just put some dots out there and said, here are some potential locations. It's not that the city of Brandon owns those locations, but said if you were going to explore more water from this aquifer, we can put these wells out there. These well locations have not been identified in terms of a specific site. But we needed locations in order to do a cost analysis of what it would cost to put wells in there and then bring them to the treatment plant. Is that fair to say?
Yes. The well that's on Holly there, the dot that's on Holly, is that about where the existing water tower is?
This dot right here?
Yeah.
The water tower is in here somewhere. It's pretty close.
Pretty close.
Yep.
Okay.
Maybe this is it. This is on the south side of Holly.
That's a tower.
Yeah.
Yep.
Okay.
So again, the point needs to be made that these are not identified specific locations, that those locations would need to be. But what they were saying is if you put a spread of wells up in this area, you're in a good spot to get water from the aquifer. And
the
we needed.
pink is kind of like the honey spot.
Yeah, that's right.
Okay.
Exactly. It's the deeper. It has the greatest depth and the greatest amount of storage and potential for development.
Those are all residential areas, right?
Yes. Yep.
Except for that one up by the school.
Yeah. Populated areas.
Yep. I think this one right here is close to a green space. And this one's across the road from a green space. You know, so I think they used some judgment. They didn't put it right on somebody's house. You know, but the idea was, you know, it's possible to develop a well in this area, and you might see good productivity from there. And I think the point needs to be made that these locations haven't specifically been identified. It's in just general representation to enable us to say, okay, if this is where they could be, then we can associate a cost with that. All right? They did the same with Split Rock Creek. Here's a summary of the water quality. Dissolved solids around 500. A little more iron than what you'd see in the Big Sioux, at least in the data that they provided. Manganese about in the same range. The hardness in this 250 to 420 range, so about 400. But we also add on here radionuclide information because it's present in that aquifer, ranging between 2 and 25 picocuries per liter, depending upon the location. And radium-226 plus, oh, that's gross alpha, sorry. And radium-226 plus 228 are the total of those two in that range of 1.5 to 20 picocuries per liter. The other important part that they said was that if you would, again, zone in on the thickest part of the aquifer as a potential location for where additional wells could be put, they identified 2 additional well potential locations or areas in addition to the existing 3 wells for a total potential amount of water to be gained of about 5,600 gallons per minute from all 5 wells. And they had a big band here to basically communicate that this is a desktop study. In order to really get more information, they had proposed to do more of a mathematical model, which was a part of the proposal as a second phase in the geological work. Okay, and again, they also provided in their documentation potential locations for those wells. So the existing well number 7 is right here. This is where potentially well number 9 was. And I think what they're saying is, you know, somewhere in this red spot. And then over here is another good spot where this black box is. And they said, well, you know, potential here, but somewhere out there would be another potential location, is what they identified. So we took that at face value and said, if we are going into the Split Rock Creek, potentially we could put a pipe out to there, put a well down, wells down, and get some water. Okay? So the next question is, well, can we get that water? And water in South Dakota is utilized by communities according to their water rights. And so there was an investigation of water rights, and there are two different aquifers, the Big Sioux Aquifer and Split Rock Creek. And without getting too detailed, this summary shows the existing water rights. I don't have the water right numbers on here, but you can go right to the DNR website and observe all of those, how much water is available according to the water rights, and then also what the future remaining water right is for the city of Brandon. And what we know is that if Brandon went in the direction of more of the Split Rock Creek Aquifer, that additional work would need to be done to secure more water right in that aquifer. So that's just a recognition of how it works in South Dakota.
So if we dug the two additional wells in the Split Rock Creek, we would have to get more water rights?
That process would need to be engaged. Now it's a matter of how do you spread the existing and future water right around. Typically the licenses right now are really quite aggressive in terms of, I would say aggressive meaning that they assume you're going to take a lot of water out of that well, and it is possible to spread that license out amongst other wells and spread the utilization. So for example, if you look at this point of diversion, which is well 7, they have on the water right about a 1,500 gallon per minute maximum instantaneous draw. And the city feels that 1,200 gallons per minute is really what that well can produce. And so there's, I would call it leftover water in that water right. Same thing with well number 6 and 8. The maximum instantaneous draw is 1,993. Quite frankly, well number 8 might be able to do that. But the long-term utilization of that well tends to make you slide back more to what is the annual amount of water that you can get. What does that mean in terms of how that well is utilized, and whether or not utilizing additional wells enables you to spread that out or move it around. It's all a matter of discussion with the ENR and how they focus the water rights. But then in addition to that, there's some future water right. And if you look at the total of all of these, you're getting close to what is needed. But in some cases, depending upon which alternative you have, you might need some additional water right on the Split Rock Creek. Did I say that correctly, Greg? Yep. Greg's table. So this is Greg Hansen, by the way, and I'm Dale DeBoer. We're with AE2S. That's the introduction at the end, right? Okay, so the point is that it's recognized in the state, and it's well understood that when you utilize groundwater sources, you have to engage the DNR water rights program. And so they would need to do that regardless of well number 9 is being explored, and we don't have a license or a permit for that well in terms of its final water right. You know, there's a process whereby that goes through. And so, you know, when you look at that and look at the existing water rights and look at the amount of water available from the Big Sioux, there's quite a bit of licensed water or available water in the Big Sioux, much more than they've been able to utilize. Okay? When you deal with future water rights, you're usually in an area that is defined where that water right applies. And so these are the Big Sioux Aquifer water rights, and these numbers on here correspond with the numbers on this page. Okay? So that expansion, if you want to call it that, of the well field up to the north is within the area of a future use permit. There's also some existing wells that if they are released or not utilized, perhaps there's an opportunity to transfer those water rights. It's all pretty much at the discretion of DENR with appropriate information provided to them. This shows the location of the future water rights for the Split Rock Creek Aquifer. And as you can see, if the city intends to move to a different location, that the future water right area does not include those locations. So again, there's discussion with DENR, development of appropriate information to enable them to consider additional modifications to water rights for Brandon. The point of that whole discussion is that that is a step that would need to be taken in exploring these alternatives. And it's recognized that that's a normal part of business. Okay, so if we look at source alternatives, here we are looking at those well sources from the WSLP report. This is just a summary of that. It turns out that it appears that these aquifers have enough yield to meet that 2070 demand. It's just a matter of stepping through the hoops to gain access to that water and then to get it permitted appropriately. Then we also talked with the regional water suppliers. Minnehaha Community Water Company, actually Brandon is in their service area, and so they serve customers around the city of Brandon. And we talked with Scott Buss, AE2S, and the city of Brandon folks about what options might be. And they have provided a short-term option, a time span of 5 years after the connection's made, where they could provide a certain amount of water. We'll talk about that when we talk about the short-term options. City of Sioux Falls we had meetings with those folks, and they concluded that providing water to the city of Brandon was not an option for the city of Sioux Falls. They really have some uncertainty regarding some of their existing water source. They have some contamination in their well field, and they're concerned about the impact of that on their total water resource. And so until they get that resolved and understand what that means for them, they're really unwilling to bring on additional customers outside the city of Sioux Falls. Lewis and Clark Regional Water System, we also had contact with Troy Larson, who's the executive director there. Turns out they're just beginning the phases, starting discussions within their membership for the next life of Lewis and Clark. They're calling it Lewis and Clark 2. And so most of their planning is, well, the next phase is out to 2040 something, and then an additional phase out to 2060, and they're looking beyond that to what additional water can be brought to serve southeastern South Dakota. And they were very interested in inviting Brandon into that discussion. Part of their approach at that time was that it would be unlikely for Lewis and Clark to take on new members, but existing members can certainly consider taking on additional customers. And so that might be a route to get additional water. But that's planning way into the future, and since that future includes the time span for which the study is being done, our recommendation is that the city of Brandon attend those meetings, engage the discussion. Just like we recommend that they continue to talk with MCWC and with the city of Sioux Falls, because those may be potential future water suppliers still for the city of Brandon, depending upon how Lewis and Clark 2 works out. Okay? So that's a part of, I guess I would say, the future recommendation for Brandon in this study is that they stay engaged with these 3 regional water supplies to make sure that as opportunities arise that Brandon can understand what that means for Brandon. So given that short-term opportunity with Minnehaha Community, the real question is, should Brandon take advantage of that? What is it, and how would it compare with other things that Brandon can do to provide that would match up with that in terms of quantity? Okay? So the first alternative here is to actually do that purchase, and we'll talk about the details of that. But there are 4 other alternatives. One is, and they all have to do with getting more water to the Brandon water treatment plant from the current resource available to Brandon. So the first one is to pipe well 3, which is a part of Brandon's inventory, to the treatment plant, so it can be used year-round. Treat it for iron manganese removal and use it year-round. Utilize well 7. That infrastructure's in place. There's been, basically a decision to be made about whether or not to turn it on and how that would influence water quality, be treated, and so forth at the treatment plant. A 4th option is to utilize well 7 with the addition of radium removal technology. Talk about that briefly. And then finally, construct and connect well 9. It's an additional well source that is being explored right now. And so those became the alternatives to compare against Minnehaha Community. The maximum day demand estimates needed to be done to understand, well, how much water will Brandon need in this short term, and how well will those alternatives supply that need. So if you look at the maximum day demand estimates out of 2024, the maximum days in that 2.73 range, which is about 9,000 gallons per minute on a continuous basis. The water production rate from the treatment plant is 2,000 gallons a minute. So conceivably, the treatment plant, if it has adequate water source, could provide the water to meet that maximum day demand. It would be still stretched to the limit, but there's a possibility here. So, in order to do this, there was a cost comparison that needed to be done, and this is just a summary table showing how the costs were developed for the existing cost of water, if you want to call it that. But these costs, and this is using the existing water supply system without any additions to it. So here we have each year the annual operating costs being developed. And the sum of all 5 years of operating costs are in the right-hand column. And on the right-hand box, we see the capital costs, and there's some assumptions made here for continuous improvement of the existing system as a capital cost. And then O&M costs are simply transferred from this table to come up with a total capital and O&M cost accumulative over the next 5 years. And if you divide that by the number of gallons that would be produced by that system, you end up with a cost per gallon. This is a cost, it's not the water rate that is provided to the customer. This is a cost of production. And this is a baseline. It's a good estimate, I guess I would say. We sort of ran this by the City of Brandon folks, and is a reasonable estimate of the cost of water given the assumptions that were made here. So about $2.76 per gallon. Alternative 1 would require connection to the existing Minnehaha Community Water Company pipeline that goes down Sioux Avenue. There's an 8-inch pipe there, and that would be served from the tower that's at the north end of that, up by the industrial area. There's an MCWC tower there, and there would be modifications made for their system for them to be able to utilize that tower, if you want to call it, as the nurse tank for their production for the City of Brandon. That water for that tower would be mainly coming from the Lewis and Clark connection that Brandon has. Sorry, that Minnehaha Community has. So there's some infrastructure that needs to happen in order to make this go. Basically, this pipeline would need to be constructed to connect that pipe to the water treatment plant. The treatment plant would utilize treated water and blend it with water from the City of Brandon's treated water. So it would be treated Minnehaha Community water blending with Brandon's treated water with a little chemical adjustment to make that work. And that chemical adjustment is breakpoint chlorination of that water. So the considerations of that is that the cost that they have for their bulk customers is about $2 per 1,000 gallons. And so they offered that cost. And the other consideration is they're providing treated water. And when you look at how that blending would occur in order to keep a consistent water chemistry, a consistent blend, the treatment plant operates in that range of 1,600 to 1,800 gallons per minute. And to take advantage of the 250,000 gallons per day maximum flow that they would be able to provide, and blending it with the City of Brandon's water, that's about 230 gallons a minute flow rate when it is being blended on a maximum day with about 1,600 to 1,700 gallons per minute of Brandon's water. So on maximum day, that would be about 18 hours. So if you divide 18 hours into 250,000 gallons, you get about 230 gallons a minute. So that would be the option. Here are the cost tables associated with that option. And so we've got O&M costs, capital costs associated with that, and with the total water cost of about $3.24 per 1,000 gallons for that option. The next option is to connect well 3. So well 3 is sitting up here in the commercial area, and we assumed a pipe location to get it so it could connect into the water treatment plant. And as an interim, connect it to the transmission line that comes from well number 7 to the treatment plant. As an existing well house would need a new motor pump VFD to be able to match up its flows with what's needed. and the header piping. So there's existing water rights for that well, no additional consideration there. That flow would enable the treatment plant to operate at its max capacity of 2,000 gallons per minute. And the nice thing about this is once Brandon has that infrastructure in place, it would be usable for longer than 5 years. Whereas any infrastructure put in place for a Minnehaha Community Water Company has a 5-year lifespan in terms of utilization. There was this pipe right here that could conceivably be repurposed to be a part of treated water to supply water in this area. And so there was some consideration of that. Would have to be something that would be considered at the end of that 5 years. Alternative, so here's the cost associated with that. Alternative 2, about $2.98 per 1,000 gallons treated. Alternative 3 utilizes well number 7. The infrastructure is pretty much in place to do that. I know that there's some additional infrastructure that's being considered as a part of well 8's construction. That was assumed to take place. It's an existing well with available water rights. There, in a part of this cost evaluation, would be additional HMO chemical required to treat this water for iron and manganese and radionuclide removal. And again, that infrastructure is in place, would be available for use beyond 5 years. Here are the costs associated with that. $2.93 per 1,000 gallons. The next alternative utilizes well 7, but engages a pretreatment process. And let me jump to the next slide. There's a company called WRT that makes a radium removal process. They've developed a radium-specific media that absorbs radium. That media is used sort of like the media in your water softener, except in your water softener, you can regenerate the media. In this case, the media is not regenerated. Once it's exhausted, they come and change it out. And they dispose of that media. They're working on a process of recycling that media, but currently they dispose of that media in a regulatory fashion. And so a part of the cost of this alternative is the cost of exchange out on those media exchanges. They operate these 2 vessels. They're 14 foot in diameter. They operate them in series with each other. So this building would need to be built out by well 7. And the idea with well 7, since it has the highest radionuclide removal, is to provide a treatment process that removes the radionuclides. Essentially, you come out of here with a near zero value. Only at the end of the cycle does the radium start to creep through. We call it breakthrough. And so they anticipate that and exchange out the media.
I had a question after yesterday, we were talking about that. Is there a reason why people want to put that after well 6?
Yeah, that's a great idea. We considered those options. You know, why not engage this closer to the treatment plant? And I think the idea was, it's sort of like, I don't want to make the analogy, but you want to put this nearest the baddest water, the worst water quality, so that you can get the most efficient use out of the process. Right?
So you wouldn't want to take well 6 down? Because I don't know if it's like 6, 5, 6.
Well, 6 is in that 5 to 7 range of cubic per liter. Yeah. So the idea here is, let's utilize this in its most efficient manner with the water that has the highest radium, enabling the water that comes from that to essentially be radium, very low levels of radium. I was going to say radium free, but I won't go there. It's very low levels of radium. It essentially acts as a dilution for well number 6. That whole water still goes to the treatment plant and is exposed to the HMO treatment at the treatment plant. Certainly would be worth additional evaluation, but our approach was to be able to enable this to work in its most efficient way with the water that had the highest radionuclide. And it's also a sizing issue. So if you put it there, then you have to decide, well, how much water do you going to put through there? Because there's a certain area, your experience in engineering said these has a loading rate associated with it. So if you do that, do you size it for well 6 plus well 7? And treat all of your water with radionuclides? So there's an optimization in design. Certainly could be considered. The approach we were taking here was, how can we gain more water for the treatment plant to compete against Minnehaha community. And this was an alternative. In fact, this was then taken on into a long-term alternative as well. Great question.
Great idea.
Yep. Well, the other feature of this is the radionuclides get taken out of the area, right? And are disposed in a regulatory fashion. So rather than having to deal with the residuals, wherever they go in the area, you have this option that takes the radionuclides somewhere else.
Well, that was always the Peter mongering part of it. You want to go that far at the level of why would we use well 7 if it has that high radionuclides, and that would take that argument out, I guess. Testing at a level that's obviously lower than the SCL already.
Yep.
What was the cost on that?
The cost for the equipment is $27,000, and at that level,
2.7.
sorry, 27,000. All right, $2.7 million for the capital improvement, and that includes the on-site stuff, the building, the equipment, etc. And then there is a cost per thousand of $1.20 per thousand. And that's the cost that you pay them for this periodic replenishment of the PTR.
Is that factored into the 3.55?
Yes. Yes. So if we look down here, we see a purchased water cost. This is for the line item for Minnehaha community. And then there's this WRT service fee. This was not for treating all water from well number 7. This was only to treat the water from well number 7 that would be used to supplement the existing sources to get up to 2,000 gallons a minute. Correct? So it actually would have capacity to treat more gallons per minute than that. But the cost for service is all about how frequently do they need to come. And the larger the system, the less frequently they need to come. So this is all a part of the discussion behind it. We can certainly engage the discussion with you.
So, I don't mean to belabor this, but because we were so involved in the decision of buying well 7, building the pump house, building the transmission line, the raw water line to well 6, all the money that has already been spent, the decisions that have been made, I don't want to ask the question because I really want an answer, but would we have put all that money in well 7 and added the WRT treatment at the time of buying that, would that have been a good decision? Because we have
It would
the well,
certainly be
bought the well.
an alternative that could be considered.
If we knew that we were going to be dealing with radium levels of 25, and we had to go through what we did from a social standpoint with the issues of actually using well 7 water,
Yeah.
if we had the foresight, or if it had been planned to already use the WRT treatment system, knowing that we needed to treat that radium level, would that have been a good decision?
I would say it certainly would have received favorable consideration by someone thinking through the alternatives. Because when you ask the question about good, and good is all relative, to perspective, right? So where I'm coming back to is it certainly is a viable alternative and has the capability to enable that water to be used and take the radium out of it.
But doesn't alternative 3 allow that water to be used? It's just treated at
Yep. So it's a matter of perspective. Like I mentioned, this alternative takes the radium away from Brandon. Alternative 3
Yeah,
uses HMO to treat this water.
right.
So now you have the radium in the HMO with the resulting requirement to dispose of that. So it goes now to the city of Sioux Falls. And the city of Sioux Falls, as you'll see later on, is asking Brandon to consider alternative means to dispose of that backwash water. Now they're also considering other potential metals in that waste as being of concern. In fact, the metals in the waste, they've indicated were the concerns that they were talking about. But from the perspective of where the radionuclides go, It's just a matter of at some point they move around. You know, why not discharge them into the Big Sioux River directly? You know, and so that question came up as a result of looking at what ENR would be interested in understanding about that.
So the point I'm trying to make, again, is from a social aspect, because that is a big reason why we're here today. If that was a decision that the council were to make, or to go with that alternative, spend the extra 2.7, or 1.7? 2.7, enter into a contract with that company. My point is it eliminates the Facebook uproar, potentially, that we're not dealing with that again. Social outcry that we're putting radium into our plant, we don't know what it's being treated at. Through that option, we do know what it's being treated at. It's been proven to work. We can test the water can we test it there before we put it into the system?
Yep, part of their normal routine is to test the water that's been treated by this.
Because that's key. I mean, we can't do that right now in the plant. We can't test the water coming from well 7. It has to be treated first. And we can't test it. It takes too long to test it before it gets into the system. We don't get the results.
Yeah.
That's been an argument that I've had for quite a while. If we can test it and we put that in there and we can prove that the water is below the MCL before it goes into well 6 area or through the transmission line, we get the well, we get to use the well we've already invested the money in. We would have probably more than likely invested the money in this treatment if we were going to go down that road anyway.
Sounds like a good argument, doesn't it? Sounds like a good long-term
alternative.
alternative.
We're making a decision.
Yeah, long-term alternative.
To be able to justify why we would now spend more money on that well to use the water, certainly does seem like that would be a way we could sell it. I don't know if
Yep.
that's the right word I'm looking for, but do you disagree? We're still a committee here, right?
No, and this is devil's advocate.
You know, we're almost to a point of discussion on this.
Oh, sorry.
So what I'd like to do is get through the next couple of slides and then come to what our conclusion is.
Sorry.
Then whether to pursue the Minnehaha community idea or not, which is like a real question. So let's just get through alternative 5.
I apologize for interrupting.
Oh, no. Those all would be a part of the following on discussion. So here's alternative 5, and that's just to continue on with well 9, get more water from there, and utilize that in the treatment plant. Okay? It's unknown what its capacity might be. You know, it could be 200, it could be 400, it could be 150. It's unknown. So that's why there's a question mark. But it certainly is an alternative that could be considered to provide more water to the treatment plant. What advantage is, as we know as of now, is that it has very little to no radionuclides because it's in the Big Sioux Aquifer. There is potential for nitrate in this well. Well number 1, which is down here at the treatment plant, has nitrates between 5 and 10 milligrams per liter. But if that comes in successfully and the water quality comes in successfully, it has potential for longer-term use. Okay, so here are the costs associated with that. So when you compare those all, this is the existing system estimated water cost per 1,000 gallons. The ones in the brown represent a sort of an equivalent amount equal to each other. Alternative 2, which is connect well 3. Alternative 7, which is disconnected. Notice its cost is higher than the existing cost because of the higher cost for radionuclides and pumping and so forth associated with that. But there's just some additional cost associated with that. And then finishing well 9 has costs associated with that. So if you look at these alternatives and consider the impact on water cost and compare that with purchasing water from MCWC, which has a short life of just 5 years associated with it, or the cost of WRT at well 7, you have a basis on which to make a decision. The WRT at well 7, again, includes the cost of just providing 400 gallons a minute, roughly speaking, to the treatment plant. not utilizing that well to its fullest extent. Okay, so when we then summarize that discussion, we have alternative one, which has a relatively high cost compared to some of the other alternatives to get water up to the needed production for the next 5 years. It ends at 5 years. Now, the nice thing is it provides treated water. So it likely lower the hardness of the treated water from the treatment plant, maybe 10 to 20%, depending on the blend ratio. Okay? We can use 10% as a good number. Alternative 2 and 5 add source capacity and are relatively low cost. Alternative 3, existing well 7, requires HMO optimization for radium removal. We haven't proven that it can't do it. In the pilot study that was done, it was indicated that there is the capacity of HMO to treat those radionuclides. But certainly, it's something that needs to be tested full scale. The other thing that's happened full scale is that the media has been changed out. So now the media has been replaced by, the green sand media has been replaced by IMAR media and needs HMO for it to work successfully, as well as free chlorine residual onto the surface of the media. So there have been changes in the treatment process at the plant to enable the IMAR media to work successfully. So that's all a question now to be answered is, with the existing state of the facility and the potential for this higher level radium to come to the plant, will the HMO successfully remove those radionuclides down to below the MCL? Okay, that's open, from my perspective, an open question that has some science supporting the fact that you should be able to do that with the existing treatment process.
What are timelines on some of those? Like, obviously, WRT is going to take longer because you need to build some infrastructure there. You know, I mean, it's solid. It's not a high maintenance. It's solid infrastructure.
Yeah.
What's that look for a timeline? Because if it's 5 years, that's fairly, as I age, it gets faster. You go so fast. So 5 years doesn't seem like, so if it's going to take 2 years to get that done, or a full year to get that done, it just doesn't, what does that look like?
So all of these alternatives have a timeline, right? The shortest timeline potentially is alternative 3, but would require a bit of experimentation to ensure the treated water when well 7 is blended with the other wells meets the Safe Drinking Water Act requirement. And that is, I would say, a factual element associated with that. But the hardware is pretty much there. Well number 3 and well number 9, it's just a matter of construction, right? Planning and construction. So if well number 3 is added, you need to put the pipe in the ground, right? Well number 5, it's in early stages of exploration. There's a hole in the ground. They're going to do a pump test on it and see what the success of that is, right? Well, alternative number 4, well number 7 plus WRT, you know, there's a good chance for a pilot to provide the assurance that the technology works with granular water. And the WRT company does those pilots routinely for systems. You can go to their website and see the results of their pilot studies and see that they've done it on water containing radioactive substances similar to granules. Okay? But then it's a matter of engineering, you know, designing, building, construction, installation, and operation. So all of these have times associated with it that certainly could incur within the 5-year time span of MCWC. But I would say that, you know, if a decision is made on a direction to go, that, you know, these other alternatives should be able to be well underway, if not installed and operational, within a year, year and a half.
And obviously, if alternative 4 was chosen, it would be long-term, like it would flow into the long-term.
Well, actually, alternatives 2, 3, and 4, and 5 all flow into long-term solutions.
And then for WRT, I know I asked this, and I don't know, I can't remember, so I apologize, but we take out the radionuclide. Is it 2?
The second is to add the WRT, radium removal technology, to well 7, utilize well 7 with water treated for radionuclide removal. Option C is to continue, all of these have the existing process as a base level of treatment, because all of these wells need iron and manganese removal, and that's the large share of what the existing process does. It also removes radionuclides as well, right? So all of these have the existing process as a base level of treatment. Option B adds WRT process at well 7. Option C adds RO to treat a portion of the filtered water flow, like we mentioned before, to remove the hardness from the water and create a treated water hardness that's similar to the surrounding neighbors. Option D includes radium removal technology at well 7 plus RO. So as you look down these options, you just see a greater degree of treatment being provided to the water. And the expenses go up associated with that. So essentially A through D, in fact, if we want to summarize that, the progression from A to D increase the degree of treatment and provide incremental better water quality. Okay? With quite a leap from B to C, because B gives you the hardness that you have right now, A and B do, whereas C takes that hardness to be similar to the neighbor's water hardness, about 200 milligrams per liter. So again, that treated water option, A to D, increasing degree of treatment. RO enables adjusting the hardness, so that's for option CD. Adjust the hardness to match neighboring systems. That will lower the salt consumption. It'll roughly, for a home ion exchange softener, cut the salt consumption by roughly half. So that would be a benefit to customers that are using home softening. They'll spend less money on salt. And then finally, all of these recognize engaging the DNR water permitting process, and for those options that are focusing on Split Rock Creek, including this additional study with WSP to firm up the understanding of what the future looks like. Additional considerations, correspondence with the City of Sioux Falls indicates their interest or the desire to eliminate the discharge of filter backwash solids to the wastewater stream. That they can view the water treatment plant as an industrial facility, and as a result, their industrial pretreatment program can apply to that. And so industrial sludge discharges are prohibited by ordinance, and they can view the backwash solids as industrial sludge. Their view is that based upon the raw water quality from wells in the system, that they suspect that arsenic may be too high for their future biosolids disposal techniques that they're anticipating. So as a result of that, they're concerned. And would, as a result of this, in the alternatives that we have developed, they implement backwash water solids thickening and dewatering with disposal in the Sioux Falls Regional Landfill. And discussions have been held, email trails and discussions and so forth with the regional landfill to understand what the requirements are for hauling to the landfill. And basically it's that the sludge solids need to pass the pink filter test. Okay? There's also in alternatives B and C the potential, well, there would be a reverse osmosis discharge to the Big Sioux River, which would need to be permitted, just like any other discharge would need to be permitted. The concern is that DNR limits radionuclides to 5 picocuries per liter at the end of the pipe. So in the blend of considering all the treatment options, this limitation on the discharge would likely be the, what's the word I'm looking for? The limiting factor on that discharge. And so we've had discussions with the permitting process folks about what are some alternatives for that permit. And they offered 3 different ideas, changing the limit, which is not likely, changing their interpretation of the limit, which has a possibility, or offering a variance. And we went through the logic with them about the fact that this radionuclide is entering the river, it's going through the system, it's going through Sioux Falls and then entering the river. What's the difference between that and discharging it to the river? And it's not about that. It's about the discharge limit. And so that discussion has gone on. And so in implementing these, it's recognized that that discussion would need to continue, and there might be pilot testing, additional river testing required in order to implement an RO discharge. Okay? So that's recognized as a part of implementation of that option. Just like moving into the Split Rock Creek for more water. What are the limitations of that? And then finally, if you utilize well 7, it certainly will affect costs, either with higher amounts of HMO required, or if the WRT option utilized, as costs associated with that. And it's just a recognition. It's not necessarily an advantage or disadvantage. It's a recognition. So let's quickly go through these alternatives. And basically, the maps here show the infrastructure that was used to do the cost calculation, right? So we took the potential locations that were identified by WSP for the additional wells in the Big Sioux Aquifer. Now we're in Alternative 1 series here. So these are the potential locations for wells, simply to create a cost estimate for doing this. With the header going through the city to well 9, collecting that well, and then bringing that to the treatment plant. In addition to that, there's additional well requirements, long-term and additional well, and again, this is just a potential location. It's not necessarily the location. But this alternative simply means moving into the Big Sioux Aquifer, utilizing the existing treatment facility process, expanding the facility to meet the future demand out to 2045, with the option at 2045 to do another expansion to get to 27. So the main things here are we need the infrastructure in place to put in the wells, bring them to the treatment facility to meet the demand. And the focus here is out to the Big Sioux Aquifer with additional water coming from Split Rock Creek to make up the needed deficit to meet the demand. So all these pieces here are part of the description, the infrastructure, and so forth. Alternative, and these are the costs associated with that. I'm just going to throw these up here. You'll notice that there's an O&M subtotal, capital cost subtotal, and this present value is the present value of the capital cost plus 25 years worth of O&M to bring to a present value so that these alternatives can be compared against each other. In addition to that, we have an average O&M and an average cost of the capital improvements that can be looked at in terms of comparing these against each other, more for a budget process than anything. Alternative 1B, similar idea. Utilize Big Sioux Aquifer wells with supplement from Split Rock Creek. The main thing here is that Alternative B installs WRT at well number 7. Okay? Everything else is pretty much the same in this alternative. Right, Greg? Okay? So Alternative B has costs associated with that. And of course, if you look here, there's this WRT service fee. There's other things. And well 7 is quite sparingly used in this alternative just to make up the needed requirement or additional amount of water versus using it full out. So there's sort of a low-end version and a high-end version for this. If you see well 7, being used in a big way, you can ramp up that service fee. So now this alternative 1B2 is we're going to utilize well 7, we got the treatment, we might as well utilize it. But if you do that, you're going to pay more for regenerating that material. So there's a range in values here for O&M from a minimal usage of well 7 simply to make up the water needed for the demand to a maximum use of well 7 because it's there and we can get good water from it if we utilize WRT. And so you'll see this range in costs associated with how much well 7 is utilized in this alternative because you have the WRT treatment. The remaining costs are in this time span between 2020 and 2045, capital improvements needed to implement this alternative. Alternative 1C, again, we're back in the Big Sioux Aquifer, but now we're with reverse osmosis. Reverse osmosis needs a disposal site for the concentrate. So again, we picked a route to get to the Big Sioux River. That route could be through this residential area. It could be down and over. We picked a logical route for the purpose of creating a cost estimate, right? And so that's an additional feature. This one also includes then an RO system to treat a part of the water flowing from the treatment plant in order to blend with other water to get a treated water hardness that's similar to the neighboring communities. These are the costs associated with that. So here you can see the treatment plant bumps up quite a bit here because RO in a treatment plant brings up a treatment facility cost. Whereas in the prior one, the treatment facility cost is down here around 10 million. But you also add to that the WR3. So your treatment capacity is probably $12 million, $13 million for treatment capability in this case. In this case, because you're doing RO, it's a little bit more expensive. But all this other infrastructures to get wells piped to the plant and so forth. Alternative 1D, utilize WRT at well number 7 in addition to RO. So you see the RO discharge pipeline here, WRT being used at well number 7. And 1D is going to have two different levels of O&M costs depending upon how much well 7 gets used, right? So this is at the low end of utilizing well 7 just to make up enough water needed. And then the high end says, hey, we got well 7, we're gonna pump that baby. Remember, these are costs over 25 years. So it's the cumulated O&M cost over 25 years. You look at that and you go, electrical, 4 million? Yeah, that's 4 million over 25 years for electrical. And the purpose for doing that is to enable these costs to compare on an equivalent, present value. You have to bring all of those costs to the present, and that's why you need to understand what these costs are for the total life of that. Okay, alternative 2, the A, B, C, and D are just like alternative 1. The only difference is instead of seeing this pipeline go up and collect water from wells in the Big Sioux, the focus is on Split Rock Creek, right? So again, assuming the studies enable Split Rock Creek to be developed. I'm really sensitive to your thing. So I'm going to
appreciate that. That's very, very important.
Yeah, well, and you'll see that it's mentioned in the conclusion that needs to be studied in order for that to be confirmed. All right, so here we are. At the treatment plant, it's the same as what we have right now. It's just expanded to meet additional capacity. Okay? And you'll see in this case, this hypothetical location of Split Rock Creek, this piping needs to be put in place to connect it to the plant to get the additional water. These are the costs associated with that. It's alternative 2B. Again, we're looking at well number 7, putting the WRT in place for that, and then continuing to use the existing treatment process at the existing treatment plant. Here are the costs associated with that. And again, we have this range in operational costs for the WRT technology depending on how much it's used. Alternative 2C, again, is with RO to enable us to match up hardness with the neighbors. Still continuing to use existing, but you can see out here we need more water because RO has a concentrate stream. So in this case, you'd need to reach out into Split Rock Creek to get an additional well right at the end of that 25-year time. And then that would continue on to supply water out to the 70-year time frame. Okay, I'm sorry, the 2070 time frame. Alternative 2C has these costs associated with it. This is the RO system again, so you see the RO planted here. Alternative 2D, again, utilizes WRT at well number 7. Brings that water to the treatment plant. We've got the RO discharge line. And the O&M costs associated with that, as well as the capital costs. So these costs all need to be developed to understand the cost requirements for each of these alternatives. And this is a summary table that summarizes what those alternatives are. Yeah.
Before you get to the summary, back up a couple of slides. One more. You're running your RO discharge into Big Sioux.
Yes, sir.
Length of pipe would be an issue. Could you run it over to Split Rock Creek?
Yeah, it's interesting. Thought about that concept, and Split Rock Creek has different discharge requirements. The Big Sioux. So that would be a part of the discussion. Is, hey, we're close enough to the confluence with the Big Sioux. You're going to treat this like the Big Sioux, or are you going to treat it like Split Rock Creek? It's all part of the discussion. Absolutely. Hey, this is just a short distance. Why not go here from there to there? That's a shorter pipe.
But yeah.
Yep, it's all part of the discharge.
If the discharge, if the restrictions would be different in Split Rock, and that would, yeah, cost savings on pipe.
There absolutely, there is a difference. Okay, so we can, this, on the right-hand side is the summary of the present value of O&M plus capital costs for each of these alternatives. And you can see for those alternatives that utilize WRT, these ones with the green check marks here, they have this range of O&M costs associated with them, which then reflects in the total costs. So why do we need this? We need this to compare these alternatives against each other from a cost-effective standpoint. So this gets into the costs. We'll do that blend after we discuss briefly the KT analysis. So part of the desire in this study was to understand not only the cost issues associated with this, but the other concerns that the city of Brandon might have in implementing those alternatives. So we have a KT analysis that was done. This was a part of the approach to do this. So in that KT analysis, you consider alternatives. The alternatives are judged against what they must do. So these are the three things they must do that were decided basically by the team. They have to provide additional source capacity. They have to be treatable to meet the Safe Drinking Water Act requirements. The water must be treated also to meet iron and manganese secondary standards. So those were the base level of judgments against which alternatives were compared in order to be able to say, yes, we'll consider these further. And then this is the list of desirable objectives. So if you look here, there's stakeholder impacts with some sub-objectives under that, a source treatment operations category with sub-objectives, system characteristics and operation with some objectives, and then implementation. So as you think of these alternatives and think about all the factors required to engage in, these are some of the things that were developed in terms of concerns and priorities. Last time we were with the committee, we went through an exercise with them to understand what their weights would be on each of these topics. So each number here represents a person on the committee who basically submitted their weighting for each of these topics against each other. So the main categories of stakeholder acceptance, treatment operations, system operations, and implementation were judged against each other. And then underneath each of these were the objectives were also judged against each other. So you can see, for example, this person number 2 said public safety was number 1, give it a 10. Next was City of Brandon impacts, customer impacts, and then finally construction. Whereas person number 2 said, no, customer impacts as the highest priority, City of Brandon next, and so forth. So each person could put in their vote, if you want to call it that, or their priority rating for each of these. In addition to that, the Brandon staff did the same thing. And the city's A2S staff did the same thing. There are 3 of us working on this project. So all of these numbers then were consolidated. The Brandon Water Development Committee weights, the Brandon staff weights, and the A2S weights were averaged. Basically, the staff and the group, I guess I would say, actually this was presented to the city council as an idea, and so we moved ahead with the approach. And so after the averages is done, then they're normalized so that the one that had the highest average weight was given a normalized weight of 10. And you can see under each of these subcategories that one subcategory, one sub-objective is also given a 10. So 10 means that that has the highest interest or the highest priority should be given the highest weight, right? Then another focus group got together and scored each of the alternatives against these options, against these criteria. And so you can see here in this table, the alternatives 1A through 1D and 2A through 2D were all scored, right? So here we have a score, and you can see that, for example, for customer impacts, alternative 1D and 2D received the highest score. The most weight was given because to D because it produced the best water quality. And you can see that alternatives producing a lesser good water quality scored lower. You can see down here, if you look at maintenance, the simplest system, which would have consequently the least amount of maintenance issues associated with it, received the highest score. So the existing treatment facility basically is the lowest level of treatment, the lowest level of mechanics, and so forth. And then so depending upon the objective and the category, one alternative may score high in one objective and score low in another objective, based upon the ranking that was developed by the committee. They did a great job. So in looking at these scores and then multiplying times the normalized weight of the objective and then also times the normalized weight of the category, each of these objectives received a numerical score. They were all added up to the category score and then totaled to give the total performance score. On the bottom, you can see how they are ranked relative to each other. The ranking is simply the lowest score divided into the score of that objective. So for example, the lowest score is 8,166. The highest one was 8,829. You divide that by the lowest score to get the highest score was 9,478. Divide that by the lowest score to get the ranking, the performance score for that objective. So the one that had the highest score received the highest performance score, right? These are pretty close to each other, actually. But it is a function of the approach. And the approach including the stakeholders in the discussion of how important each objective is relative to other ones, and then how the alternatives are assigned scores to that. So I think the folks did a great job of coming up with this. But what you see is that based upon this performance score, there's not a lot of difference in some of these. There is certainly something that has the highest score, 2B. What would 2B be? It's using the Split Rock Creek as the main focus for water supply and using WRT at well number 7 and treating the water at the treatment plant using the existing process. Received the highest performance score. In fact, this is summarized actually here. The non-cost scores range from 0 at 1.0 to 1.16. Highest is better. 2B is the highest. 2D was second. And then these three were about the same. So then, along with that, we can blend in the cost analysis. So the cost analysis is providing the present value cost, the present value of O&M for 25 years, and the present value of construction to do that alternative. So you can see that the highest cost alternative, that was from those tables that I showed you earlier, is 2D. And this is assuming low well 7 usage. It's also 2D assuming, and 1D assuming the highest well usage. Okay? Whereas the lowest cost is option 1. And mainly it's related to the extent of the treatment that's provided. The more treatment that's provided, essentially the higher is the cost, generally speaking. Some of these are pretty close with each other. If you look at this one right here, 2B versus 2C, you can see that they're within a couple million when you bring all those costs to a present value. So the green one here receives the highest combined or composite score, which is found by dividing the cost performance score into the KT performance score. Now why is that? It's that because cost and non-cost performance were given equal weight, if the cost had a bigger difference between the low and the high end, it's going to dominate. It's going to take over that smaller difference between the performance scores, the non-cost performance score. And so that's what happened here. Okay? There was a little difference here, high well 7 versus low well 7. And this had to do with essentially the cost of WRT being a higher weight, if you want to call it that. So the cost of the WRT jumped up quite a bit here compared to here, right? So if you look at the cost scores, they range from 0.56 to 1.0. In this case, low is better. The cost and non-cost score were given equal weight in the composite score. So again, we've got the summary. The highest ranking alternative is 2A. With low well usage, 2B is the second. And then we've got the second is 1A. So that is a way to rank these alternatives against each other. when it comes down to it, it's also cost to the consumer and benefit to the consumer that enables you to make a judgment on perhaps which one you might select. So let's look at another approach to these costs. Here we have the annual capital improvement cost. This was from this table. Right here, we've got these values right here. We've got the construction costs in millions of dollars. And if you take that value and then do work on that to understand what the payments might be to implement those in phases, and there's actually quite a bit of work into this. It's not like all these improvements are going to be built tomorrow or at the start of the project. They are built in phases. So you might have a high-cost element built in the first 2 years and then followed by a couple of lower-cost elements to be built later on. And those costs all need to be worked into what that average annual capital improvement cost number would be. So you just don't take this number and divide it by 25 and get this number, right? You have to buy these things, so there's loans and so forth, those kinds of improvements necessary. So what we've done here is shown an average value of the capital costs so that they could just be compared against each other from a budgetary perspective. So that's what this plot is right here. This is the annual capital improvement cost of these alternatives. We've got these sub-twos. This is high WRT versus low WRT, high WRT versus low WRT. You see these costs are the same because the capital cost of WRT is the same in both those alternatives. But when you look at the O&M costs, when you utilize that WRT more, the O&M cost associated with it jumps up. So again, this is the average annual O&M cost over the time span of 25 years. So it's like close to mid-time span is what you might see these costs, roughly speaking. When you stack them against each other, on top of each other, this is the average annual capital cost and the average annual O&M cost. So you can see the total annual cost comparison of these alternatives. Here's what's interesting. Some of these start to get close to each other, especially if you look here in the Split Rock Creek alternative, where this alternative 2B2, which is utilizing WRT, and the existing water treatment process is similar to using RO. Okay? So finally, one might consider, well, what are the impacts on customer bills? You know, this is essentially where the rubber meets the road for many communities. And so the assumption was made that a customer might use 6,000 gallons per month on average. This is a family of more than just one, I can tell you that. Or it might be a family of one that has a big lawn. Okay, it depends. But we found 6,000 gallons per month is a reasonable test number to compare. Inflation rate of 2.5% is assumed across the 25-year time. Capital projects funded at 3% using a 25-year loan. It's a reasonably current value of the SRF. If you choose to use a different borrowing technique, bonding and so forth, you would have a different value. But to compare these alternatives against each other, we assumed an SRF idea. We assumed all labor, maintenance, and so forth that are needed to operate the water system are included in this. It's just not the labor and maintenance to run that treatment process, but it's to run the system. So that's included in here, plus about $350,000 for additional improvements to bring some reality to the fact that you might need to replace things here and there, pipes in the system, other kinds of things. So if you compare these alternatives against each other, this was our estimated impact on the monthly water bill for these improvements over the next 25 years. This black line is inflation. So if you simply adjusted your water rate to account for inflation, estimating inflation to be 2.5%, who knows what that'll be, this is how the water bill would rise. Currently, you're somewhere between $35 and $37. Maybe that was last year's, for 6,000 gallons of water used. And that would be for a residential customer with a 3.5-inch meter. 5/8 inch, sorry. 3/4, 5 inch, yeah, something like that. 3.5-inch meter would be a big residential customer. Okay, So you can see that some of these alternatives have a water rate increase slightly above what the expected rate of increase might be just to account for inflation. You could also say, well, no, you got to compare against the flat line. And I would argue, well, that's not really realistic either, because you expect your cost of work to go up. You're paying more for salary. You're paying more for power. And so you really should consider inflation as a part of the comparison. So you can see that these alternatives down here, basically the 1As and the 1Bs, 2As and 2Bs are collected down in here. If you look at this dark blue line, I want to draw your attention to that. That's alternative 2C. And this dashed blue line is alternative 2B, utilizing well 7 pretty aggressively. Right? So, I heard some interest in well 7 with WRT as enabling you to engage that well. Another way to handle radionuclides is to reject them with RO. So utilize the HMO treatment and come out of the HMO treatment process with the water that meets the Safe Drinking Water Act. Utilize the RO to improve the water quality relative to hardness. Blend that together, and that's an alternative. And what's interesting to us is to see how those two alternatives are close to each other relative to the cost of implementing them. Those are all assuming that more weight is put into the Split Rock Creek Aquifer. I understand, okay? So here we are looking at the average monthly water bill. So if you take a midpoint in here, right around 20, 30 something, and it might range either way where the average actually turns out. Because in some of these alternatives you have times where there is an additional piece that is implemented, maybe an additional well is implemented to make sure you met the demand. It's all phased in. So we don't have smooth lines here, we have bumpy lines because of things that are brought in, things get paid off and so forth. So these dark blue lines represent the average monthly water bill for each of these alternatives at about year 20, 30 something, right? Or you take all the averages of all that and just average it out so you can compare these against each other, right? This black line is your current water bill. Okay. This dashed line in here represents an estimated impact of building the 2 water towers that are proposed for the community on what the water bill might be, making assumptions as to how they're financed and so forth. The reason we put that on there is to recognize that other things are happening. It's just not the treatment plant. There's a core area work that's being done. And I think part of the funding for that is coming from the water fund. That's not included here. So as the city considers these alternatives and considers the rate impacts, it's just not about the water treatment improvements. It's about other factors that are influencing the total water rate that's going to be for the city of Brandon. We did not know what all of those influences are. In fact, some of those are still in discussion and planning and so forth. So we had, at a minimum, to recognize the differences in costs. So coming back here, you can see that there's a big ramp up to a value here, and that's essentially in preparation for the treatment plant, which could likely be built in 2023, 2024, in that time frame. But thereafter, the expansion to the treatment plant is taking effect, and you need to pay off that loan. So you can see that all of these have a ramp up, and then they sort of flatten out a little bit, right, after that. So if you compare these against each other and look at comparing that water rate against inflation, by 2024, the water rate, if you just adjust it for inflation, is at $40. And this option up here is at $60. These options down here at $50, in that range. These options up here seem to get pretty costly. So this one right here, this green one is alternative 1D. The purple one is alternative 2D. And so they have sort of a little lift in expense compared to the other ones. It's a matter of choice as to how extensive you want to treat the water. So, conclusions coming from this. Engage the WSP quantitative model phase before continuing further with design of these to ensure that you have a long-term water supply. But the idea is, due to the expense of development and the productivity of wells, the Split Rock Creek options came in at a lower cost. And as long as that water can be treated to meet the requirements of the community, the goals of the community, and you have options, one of the things that came up even today is ensure reliable radionuclide removal. Paul, that's where you were going with your discussion, weren't you? It's like, hey, if we just turn on well 7, we ensured that the treated water is coming out of the treatment plant is going to meet the goal. So that's a part of the selection, is to ensure reliable radionuclide removal. With RO, you have another barrier to that water. So essentially you're engaging a second barrier to treatment, to remove radionuclides. With WRT, you have an additional barrier. So other than the A alternatives where you have the existing treatment process, each of the other treatment processes improve water quality by, number 1, having an additional barrier for radionuclide removal, and number 2, for B and C and D options, having reverse osmosis that gets you to a water hardness that's close to what the neighbors are. Okay, so coming out of this, our conclusions are, it would be appropriate for Brandon to consider alternative B or C for treatment. If the costs for that, in conjunction with other costs that are being imposed on the water rate, can be appropriate for the city of Brandon. 2B enables higher use of well 7, as compared to what is being used right now. 2C enables higher use of well 7 as well, because you're getting additional radionuclide removal. But in addition, 2C engages reverse osmosis, enabling the raw water, the treated water hardness to be similar to the neighbors. It's also recommended to connect well 3 to the water treatment plant. From our perspective, that is, again, a water source that's available that's being sparingly used. Again, with the understanding that all of this is checked against this next level hydraulic model, so that we're assured of the long-term reliability of this water source. Okay? Continue well 9 exploration and development. Early indications are that it can be a productive well. And then finally, continue engaging the City of Sioux Falls, Minnehaha Community, and Lewis and Clark Regional Water System to look at longer-term regional water options. Right? And to me, that's just a normal part of diversifying the portfolio of water supply available to Brandon. Who knows how fast Brandon's going to grow? We did a pretty extensive, I would say educated estimate of what that is. But who knows what other factors may influence growth in Brandon. Whoops. So within this framework of understanding the availability of water, that would be really the next phase, is to engage that process. But included with that would be the other considerations. Some of these other things need to happen relative to discussions with Sioux Falls, relative to waste disposal, discussions with DENR on additional possibilities for RO disposal, to understand where that all needs to go. A discussion with DENR about the anticipated additional requirements from Split Rock Creek. What does that mean? City of Brandon can choose a level of additional treatment. And our suggestion is seriously consider either B or C as an additional treatment option. And then finally, understand the backwash sludge disposal and dewatering system. And really that's a pathway that cities encourage in Brandon to go if they continue to treat their own water at the treatment plant. So those are really the conclusions. In a nutshell, it's further investigate Split Rock Creek as a longer-term water source, and consider either the WRT at well number 7 as an additional treatment to mitigate radium removal, or to do radium removal, or reverse osmosis if you're interested in additional treatment with the treatment plant. Okay? Discussion. You know what, I don't know if I hand it over to you. I know we're sitting here at 8:15. In terms of how you'd like to go from here. Those really are our recommendations of the direction that we're going.
We have a whole lot of discussion here, but does anybody have any questions that he hasn't answered? Okay, any thoughts on what your recommendation would be? I guess one of the pieces, this is just coming from the other side of my mind here, is that with the RO, I struggle with that waste piece because we're talking so heavily about conservation and be responsible with watering your lawns and really have some know-how about maintaining your toilets in your home and leaky faucet. Like you're really talking about that, but then as a city, we're going to throw away a quarter of the water. Like, you know, can
It's
we
not,
do
yeah,
the same
just,
thing?
yeah, just to clarify, it's not a quarter of the water. It's a quarter of the water that's approaching the RO system. So it ends up being less than 25% of the water that's being treated, closer to like 10%, right?
Okay, still that.
Yeah, oh, absolutely.
We're
As
still
opposed to the
wasting.
90% that we wasting if you do it.
Right.
So in that discussion, it's always about, it includes the overall impact of if you improve the water quality, maybe there's less waste at home.
Right.
It's the overall big picture, but I certainly appreciate, I just wanted to make sure that the facts were on the table.
Yep,
Regarding
totally.
that,
Yeah, I appreciate that. Yep. Do we know how, like, do we know an average of households that have RO? Is that even tracked, or is that like a self, you'll like do something yourself? So RO is different than just a regular water softener, right?
Yes.
Okay. Because, so you're talking about reducing salt. Well, looking at the thing, in order to do BOR processing, increases the monthly bill about $13 to $15 a month. Are you really going to save $150 a year in reduced salt?
Yep.
I
So
mean,
the,
that's a lot of bags of salt.
yeah, it sure is. And so when you consider the RO option, the increment you consider is that cost relative to the cost of expanding the existing treatment facility to meet the demand as well. So it comes back to, if you're comparing costs, looking at the impact on the bill. And this is, I think, where you're coming from.
Yeah,
right here.
there.
So the gap, if we just take alternative 2B, this blue line right here,
Yeah.
and compare that with alternative 2C, this is the additional cost. Am I saying this right, Greg? It's
Yeah,
the
that's
additional
what I was-
cost of RO.
Yeah, that's what I was
And
looking
so
at.
that's about $10. $10. See, we're at 52 to 62. It's about $10.
$10 a month, so
Yeah.
$120 a year, and you gotta save that
Absolutely.
much in salt.
In the front end, by the time you get out the other end of that,
It's-
now it's
It's a
pushing
big
$32.
difference. Yeah, it's a big
Yeah.
difference.
So what's the cost of salt in 2045?
There's still an increment, but yeah, it's lower.
Yeah,
So
I know.
we are not advocating that the cost of RO is going to offset totally the cost of salt savings.
Right, and I don't want people to be misunderstanding the fact that, okay, we're gonna put in an RO to get the hardness down, well, now I don't need any water softener in my house anymore. And they
It's a
quit
personal
doing
choice.
that, and then it's not soft, and then
Yeah.
they're complaining because they're paying more and it's not soft.
And choosing that alternative definitely is an educational process for customers to understand, now that if I have softer water, what does it really mean?
Yeah.
It can mean not only a savings in salt, but if you're using hard water, it might encrust your hot water heater, your water heater, not a hot water heater. It'll encrust your water heater faster. It can cause incrustation in other things like plumbing and so forth. I don't know if you see any scale buildup at all on faucets and things like that. You have softened water.
We have a water softener.
Yeah. So there's other impacts to this. And so those are all a part of the educational process. a move is made to consider that softening idea.
Really big too, is that RO emission softening also improves every 99% increase faster too. So it's not just the harvest, it's also the nitrate or the future enhancements that will help us.
Yeah.
And the
Treat
RO,
those more.
the RO compared to the HMO,
Yes.
which is best?
RO will definitely provide more degree of treatment. Yeah. So the HMO mainly is removing iron manganese and radionuclides. Those are the main things that are being removed.
And
Everything else pretty much passes through sulfate hardness and so forth, passes through that process.
Hearing the conversation, getting back to Paul and the WRT, I personally like 2B because 2B incorporates WRT from what it looks like here anyway. And that at the high school. And up here,
So be aware, if you go with alternative 2B, this would be the cost of that if the well 7 is used minimally. In other words, it's
Right.
used to make up the demand, but you're still focusing on well 6 and the other wells in the inventory primarily utilize that.
right,
If you bring well 7 up to its full capacity, then the cost gets up here
right,
because that's directly related to how much water you produce.
right.
And given the wisdom of our audience members, understanding that the radionuclides in well 7 may or may not go up, we don't know. You have an idea?
Your screen and the quartzite wash.
Have the radionuclide levels remained constant in the other split rock creek wells?
Reasonably so.
Reasonable.
You know what, they're,
Not a little.
yeah. So much of this has to do with how where they are in the aquifer, number 2.
Right,
And
where
then,
your screen is, where you're pulling water, the stratigraphy of the aquifer.
Exactly.
The extent of the aquifer, that's where I keep getting hung up on, is it's a confined aquifer.
Yeah.
You have a limited amount of water in there and you haven't defined yet how much that is. If you add a Valley Springs pulling out of there, if you add an Sioux Falls pulling out of there, now you've really
Yeah.
tightened up the quantity that you're going to have.
you're exactly right. And so this next level of WSP work to understand the long-term yield from that,
Right.
including, and to me, it's also about drought impacts. Now,
Yeah,
if you're saying there's zero recharge, well, nobody cares about drought because no water's entering the aquifer from anywhere.
right.
So it can be dry, it can be wet, and there's no water coming in.
Yeah, if you're going to put all your eggs in the Split Rock Creek
Yep.
aquifer, you really need to know just
Need to know that.
what you're dealing with and
Exactly.
what the forecast
Totally
of that
agree.
might be.
Well, and that's why I kind of like 1B better than 2B, just because we're spreading it around. Plus, if we continue conversations with Lewis and Clark too, as an additional long-term source to come in, then that would be a backup kind of thing.
Yeah.
I don't like just strictly using the Split Rock aquifer.
Right, but then you also have to remember, if you're using the Big Sioux, now you're a official aquifer.
Yeah.
And so you need to be careful of
Drought and,
what,
yeah.
wellhead protection and what goes on the ground.
Well, I would be very concerned about drought impacts on that.
Oh, yeah.
Yeah.
Especially the location that you were looking at as a prime
Yeah.
location. And even if you're thinking about this, with the current well field
Mhm.
down there and, adding next, those are just things you gotta think of.
Absolutely. One of the things is, how did the committee who was ranking these or scoring these consider those factors? And there were some concerns about long-term security and flexibility relative to both of these. And let's see, supply and treatment redundancy, there's one more factor here.
Yeah, so looking at that, they want good water and they want it for a long time.
You got it. That's essentially what it's about.
Yeah.
And in fact, when you look at the scoring and the ranking of the community, what was that? That shouldn't surprise you at all.
No, who doesn't want that? Yeah.
We didn't really need a
Good
study
morning
to
for
tell
once.
us that.
But here's what's,
At no cost.
here's what's helpful, is to have something on paper that
I know,
documents these other considerations.
yeah, I know.
And so, I think this fills a gap in getting from where we started to where we are now, in providing additional insight into these alternatives to look at.
I am very impressed with the work that you have done, and I think that provides this group with a lot of knowledge and information. So,
Yeah.
I think you need to look.
So, it gets back to looking ahead. There's no doubt, and I think this is sort of looming over the whole thing, is that Brandon's running out of water, right? And right now, you're getting from now till the next whenever as a result of conservation. And I can't applaud you enough on doing conservation and helping water management. It's a big deal in terms of extending the life of your water supply. And that can't go away. It has to actually be improved.
It has to expand.
Yep.
That's, yeah.
Right.
So that's a part of this whole thing as well. But, basically we're looking at the water resources that are available, looking at how they can be utilized. And that's really what the study intended to do. That was our job.
Choices. Yeah, shallow or
Yeah.
combination.
Combination.
You
Yeah.
only have two sources.
That's right.
Like a third, but the third is
Well, yeah.
undefined and unreliable.
Right.
And I just, my 2 cents, and I get they can't commit beyond 5 years. That makes perfect sense. That's very understandable. But MCWC then becomes a third source.
Where would you put Lewis and Clark? I mean, I think they're way down the road, but, right, but Brandon definitely needs to be in those conversations.
Right.
As soon as
You
possible.
need to be part of that conversation. The initial conversation on Lewis and Clark, Grande, we left, I thought it was going to be Grande, but there you go. It is, as Dylan mentioned, the working thought is that the existing members, Lewis and Clark 2 would be made up of existing Lewis and Clark members
Only.
only.
Okay.
In part, and this is, again, there's been basically just a very couple of short early meetings. And what's stalling them right now is trying to figure out how to, if you bought Brandon on board as a full member of Lewis and Clark, and unless the system is completely independent of the original setup, which is unlikely, you got to figure out a way to get Brandon up to an equity position.
Right.
So that, what does that cost? There's been a discussion, you guys maybe probably dealt with this on the wastewater side, looking at some of the communities to the south of Sioux Falls, and they'd love to look up at the capacity there, but Sioux Falls wants them, you need to buy in. We paid for it, and now you want to draw only the benefit from it. And the response was a rude hand gesture. That is a very similar, that's, I think right now the starting point with the current membership is whether it's the money we invested or the federal money that we were able to line up, because we stuck with it, yada, 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 to bring on Brandon would be phenomenally expensive for you guys. And in a few instances right now, another likely target opening like it's Canton is currently getting its water from one of the Lincoln County rural water systems, which is a member of Lewis and Clark. So if Canton becomes a Lewis and Clark member, Lincoln Rural Water loses 50% of their customer base. They're not, surprisingly, they don't really think that's such a great idea. And so I think the likelihood, I think it was on one of your slides, that right now, all the caveats that are there, the best likelihood for Brandon being hooked up with Lewis and Clark 2, benefiting from Lewis and Clark 2, is being identified as a future customer of MCWC and identifying the needs, what would it take to make Brandon whole, and that would simply be added MCW sees as their need from Lewis and Clark too. But I come back just to the short-term part of the connection. It's a third option. Yes, it's a little more expensive, and yeah, it may not be functioning after 5 years, but at some point down the line, 10 years from now, there's a pipe connecting two different systems. And something that's been a huge push in most of the regional systems is interconnects. You know, I mean, MCWC is hooked up to Lewis and Clark. It's hooked up to, I don't think it's hooked up to King Brook. It's hooked up to Big Sioux. Big Sioux's hooked up to King Brook and MCW.
Yeah.
Perkins to Louisville. I mean, they're all interconnected, so that the stuff hits the fan for a short time. There's a way to move water from point A to point B.
Well, just considering Brandon's location,
Yeah.
the options for Minnehaha would be to bring water from their Lewis and Clark.
Right, you have to come
Point,
over, right?
or from their water treatment plant. Those both can supply this area.
Yeah.
The
Yeah,
water
it's part of the
treatment plant
service,
supplies
it's part of the
this
service area. And
Or
it's-
Lewis and Clark came in. I guess, to sort of wrap that discussion, other people can chime in. Regional water systems and rural water systems always start with a certain clientele in mind, and they start with a certain water usage of that clientele. It has been a policy of the state of South Dakota to encourage communities to hook on to rural water systems as a matter of a part of their facilities planning effort. You need to evaluate that option. I think the idea is then primarily to encourage smaller systems, which might have resource limitations, to do that, to enable them to have a longer-term source of water quality. My concerns about doing that is, fire protection, all that kind of thing needs to be ensured in a community. But aside from that, that has been a modus operandi for rural water systems. Who can we connect? How can we expand? How can we add on that customer as a part of extending their reach and diversifying their customer base so that they have, they love a community that comes in with a solid, continuous flow rate. Because now they can plan for that, keeps their water fresh and so forth. And so that's been a normal operational mode of rural water systems in the state, and it's been very successful. The difficulty with Brandon is connecting into that, right? And basically where we came to was at face value, the board and Minnehaha community said, for 5 years you can do this, no guarantees beyond that. And so from the perspective of Brandon, it's like, did we put our resources into that? Or we have some additional improvements we can make to advance our own resources, right? Whether it's, additional water from the Big Sioux Aquifer or from Split Rock Creek. And so what does that mean relative to this short-term idea? The pipes in the ground from from Minnehaha community are likely not to go away. Right? So you bring up great points of, the connection and what does that mean for the future. And what we were trying to do is provide for Brandon an idea of what some alternatives might be to provide that water capacity. Certainly, the recommendation is from our perspective, looking at the capability for advancing Brandon's future and incorporating that into the future long-term water needs. But, it's a pretty small amount of water when it comes right down to it.
Thinking down the road also, it probably wouldn't be a bad idea to try to wrap up some of those future water rights.
Yep.
Right.
Yep. Yep.
And also the location that you suggested there.
I guess from our perspective, our objective is to finish up the report. I don't know if the Water Development Committee has a direction that you'd like to promote to the council regarding these long-term ones. If so, we'd love to hear it.
Is there an average cost that you can come up with for if we do have some sort of softening level that just adopt that based on average usage of decreasing the cost of salt?
Yep. You know, a personal homeowner using salt, you know, and of course, everybody softens differently to a different degree. But I would say the salt savings ranges between $2 and $5 per month. Is that what you're asking? Is how much do they save? What's your question?
If we soften the level, of water to the level of our neighbors,
Yes.
how much would I spend? Would I have a softener? Would I have
Yeah.
water?
So the choice of using a softener or not is always a personal choice. So it's just a matter of, you know, what benefit do I gain? Personally, I live in Sioux Falls, I have a softener, I wouldn't go without it. Even though I'm a neighbor to Brandon, and I have that great water, if you want to call it that, I absolutely require zero hardness water in the shower.
Exactly.
So my house is always going to have a softener, no matter where it is, right? So, but it's a personal choice.
You do,
And so-
I don't.
So what I did to answer this question is do a hypothetical and say, all right, we've got this customer, like these customers, 6,000 gallons per month, and you're only going to soften a portion of that, maybe 40 to 45% might go through your softener, right? So assuming that value, assuming the cost of salt, assuming the decrease in hardness from 400 to 200 milligrams per liter, of that water going to the softener, it's about $2.60 per month. Assuming 40% of the water got softened. If you soften less than that or you use more water, your personal bill. So, you know, my encouragement is for you, if you're considering what the impact might be for you, is to think about what is your salt cost, cut it in half. And that's what if the city chose to cut your price. That's going to depend on you dialing back the setting in your softener to respond to that increased hardness. So, you know, rather than me saying for the average homeowner, which I have only guessing to guess what the average homeowner uses, to me it's more of if you're considering what the impact might be for you, you take your salt bill, cut it in half, and that's approximately what it would be for you. I think that's fairer, because then it puts it on a personal level. There's some people that don't use them, some do, that kind of thing.
But the increase is still, for the treatment, the increase in the monthly bill is still what it is.
Yep.
So some people might see an $8 savings, and some people may only see $3 savings.
And if you don't have a softener, you won't see any.
Yeah, just see the increase, yeah.
I can't predict how that will affect the longevity of their softener. I'm sorry, the water heater. I don't know what that is. The incrustation in piping and so forth as a result of heating water that's not soft. All happens. So there's these non-monetary, hard to define costs that are also a cost related to use of hard water. I don't know what they are, so I can't really
Yeah.
say. And it's $3.
I mean, some people go through water heater every 7 years, and some people go through it every 20 years. It just depends on what it is.
Most commonly, it's whether or not they have a softener in front of it. Yeah. The hardness in water will precipitate in that softener, in the water heater, and form a coating on the element or the surface on the inside, and eventually muck it up.
That's why I really like the idea of that second level of treatment of the RO process.
Here's another potential idea. Design a treatment plant expansion with the option to add RO. It's basically a slab with piping to it and piping from it. You have to incorporate some of the interconnections to make it possible in the future. But basically an RO system sits on a floor. Typically there's a garage door to that area because you're almost always designing with the future in mind. And so an RO skid comes on a truck, you put a forklift on it or whatever, you haul it in, you set it down, connect with the piping and the electrical, and there you have an expanded facility. So, you know, I sort of oversimplified it a bit, but the idea is that these capabilities can be designed in. If you don't install it, that space becomes available. It's got a garage door. So what can you do with a garage door and a flat slab? You know, you can do a bunch of things with that. You can use it for storage, you can use it for trucks. Got some options there. So it's pretty common for RO facilities, the RO section of the plant to be installed with that garage door, with space for future expansion. So there's some options there in the design of the facility to enable it to happen. Well, quite frankly, it's limited in South Dakota because you have to have the opportunity to discharge the waste, right? So Yankton's new plant, HDR facility, Yankton's new plant has RO in it. That's the most recent. Windstone is a small community that's part of the Clay Rural Water System. It's a small community north Sioux City. They have an RO facility with iron and manganese removal ahead of it. Quite frankly, that's really what Yankton is. It's RO with iron and manganese removal ahead of it. Those are the two ones that come to mind. I'm sure there's some smaller communities. I know also that there are some Hutterite communities that use RO. Could be more for their livestock than whatever, but those are the main ones. It was an alternative considered for the city of Pierre, but with the Missouri River sitting right next door, it lost out financially to treated water from the Missouri River. Other questions?
There's questions, but do we have a recommendation for council, or do we want to have more people here to go recommend to council, or, well, it's only 4 of us, so. I guess that's where I was going to think that,
I need to study it and I really need
What's that?
to make an informed decision. I think you need a little more information. I think you have to know the recharges.
Yeah. Well, the way the study was envisioned, it was envisioned that that is a step in implementation.
Is that something you would figure out and tell them?
So that would be WSP's next step. So, the way the study was envisioned, the agreement was surrounding, was look at the alternatives, do this high level. If the alternative focuses on the aquifer options, then the next step is to get that next level of study to understand that.
So if you're thinking about putting the wall in split rock creek, you need that.
Yep.
If you're thinking about going big soon, you don't.
The Big Sioux cannot provide enough water to meet the future water demands. So there will need to be water from Split Rock Creek in either alternative. The Big Sioux, according to the WSP information, has, I can say, more limited collectivity in the area of the state. Now, if you go out to north of Sioux Falls, at Del Rapids, and north of there, it's different story. Different part of the aquifer, Jason put it.
One of the reasons why we kind of focus on the ones that are already from the history of some of these, what our big soup valve and
So if we were looking at just E or C, so the WRT or the RL, is there independent opinions on just those two, the performance of the quality of water that we would want to hope for the community?
I think I would choose WRT.
And not the
Not the other.
additional RL?
I like the idea of doing the WRT at
At well 7,
right?
because then if we would have to dig another well in the split rock further that way, we can pipe it in there and treat it all at the same time before it gets in there.
really expecting it to be better.
Not just because of where it's screened, if it wasn't screened there, then it would be better off, but that's, it's well
Well,
screened.
That's the uncertainty. There's no, you know, a 40, 50-year projection is predicated, again, I get you understand the qualifications, but it's all, right now, it's predicated on Split Rock Creek providing all the necessary water for as long as the projection.
There again, I don't think it needs to be the only, provided with the wells that we have in the Big Sioux and, spread it around.
I think what we've been talking about kind of hits 2B more often than any other, with the development of Split Rock Creek and the WRT and the existing water treatment plant, but then also leaving the option open for the RO down the road. I think 2B is the option we've all been looking at.
Well, that doesn't include anything then other than what we currently have in the Big Sioux. So it doesn't include any other exploratory
Well, I was
Big
thinking,
Sioux stuff coming down,
Right.
down in the future.
okay, but I was thinking we didn't want to depend too much on Big Sioux.
We don't want to depend on too much, but we don't want to eliminate it either. And we don't want all of the water that we use to come from the Split Rock.
Well, and we don't, I mean,
Yeah.
right.
Nitrate levels in the Big Sioux have proven to be increasing as well, right?
They're not going away. You know, the data are limited in terms of places other than, you know, the Brandon wells.
So what?
But you absolutely in the Brandon well have well 1 that is contaminated in that range of 5 to 10. I think it's at 7 right now or 6, right? But really that's a function of, again, the recharge area, where that water's coming from, right? So really that's the history. It's a recognized thing. You know, if you have RO available or if you have blending available,